So in the last video, we saw that the heat equation in Rn is given by ut equal to k times the Laplacian of u plus 1 over c rho f, where little k is capital K over c rho, and that's our diffusivity, and f is our forcing function. So that would give data about sources and sinks. So if the source term and the boundary conditions are constant, then we expect the system to equilibrate. So coming to equilibrium, that means that the time it eventually stops changing. So the time derivative tends to 0 as t goes to infinity. And so then the steady state is going to satisfy minus k Laplacian u equals 1 over c rho f, which is called a Poisson equation. And in the case if it's homogeneous, so no sources or sinks, then this can be rewritten as Laplacian of u is equal to 0. And that's Laplace's equation, which is the topic of the next section in the textbook. So since the equilibrium version is time independent, all you need are boundary conditions in order to determine a unique solution. Okay, so what kind of boundary conditions are there? Well, just like before, we saw that there are Dirichlet conditions. So a Dirichlet problem is going to be something that looks like Laplacian of u equals 0 on some region, and then the value of u itself is going to be given by some function specified on the boundary of that region. So that's a Dirichlet problem, and so here g is some function whose domain is the boundary. So just maps the boundary to real numbers. Then a Neumann problem. Well, this is the kind of thing that we get by fixing the value of the derivative on the boundary. But now we're in higher dimensions. So you ask, okay, which derivative? Like, should we take a partial derivative or whatever? Well, what we'll do is we'll take the normal derivative. So this will be minus k times the normal derivative of u, and that'll be fixed equal to some h on the boundary. And so here this notation du dn, this is the normal derivative. This is the same thing as the gradient of u dotted with the outward unit normal vector. And as usual, the insulated boundary conditions correspond to h equals 0. And then a Robin problem, or radiation, sometimes it's called, like Newton's law of cooling or something like that, is going to be something where the Laplacian view vanishes interior to the domain, and then on the boundary we have some relationship minus ku equals minus h u minus g. Oh, I made a mistake. That should be dutn. There we go. Okay, something like that. So a combination of the two.